And I think we try to make clear how the different space, which we can define here as a column space and the row space, how they can control different domains which are associated with a matrix. Okay, so a matrix is a mathematical construct. We can do a lot of things with it. We can use it for different reasons. And one of the elements that can help us is the concept of range, rank, and so on. Let's assume we have a matrix ABCD. Now, find D such that rank of A is equal to 1. What is D?
D is the element right there.
D is this element, yes. So let me erase this one. I can put here a number, assign a number to the fourth element, such that the rank of A is equal to 1. What can you say about the first one?
D equal to 0.
Which one, D?
Equal to 0.
No. So if rank of A has to be equal to 1, that means that the rows, how should the rows be related to each other? Equal is
I think one row has to be a multiple, one term has to be a multiple, so we cancel it in a 3 rows.
Exactly. So we can say the following: AB can be written as a constant K times CD. Okay? So this means, or, so this is one way to say it, or we can say the following: A over C would be equal to B over D, which means that what is D? What is D?
D times C over A.
Divided by A?
Yes. Okay, that's the answer. So what about here? What is A? So this is enough. So C can be random, but D should be a function of these others, and then we can always produce the second row full of zeros. So what can we say here? Who can help me here?
Can we say the same thing?
Yes. Say.
I was asking a question. I didn't understand.
So we can use the same idea. So if rank is going to be equal to 1, that means that we have only one row. The other rows, they are linearly dependent to this fundamental row. So in this case, if you have row 3, if this is 1, what should this be? So it looks to me that we can write the following: row 2 is equal to row 3 divided by 2. So then what should these numbers be?
Should be 1, 3 minus 3 over 2.
Here 1, what is here? 3?
And minus 3 over 2.
Yes. Minus 1.5. What about for the first row?
It may be the second row times 3.
Correct. So well, so let's see the following. We can use the same equation right here. D is equal to BC times A. So what should this be? This should be 2 times 9 divided by 6, right? What is this?
3.
3, because 2 times 3 over 2 is equal to 3, and also 6 times 3 over 2, this is equal to, well, this is 9. So then we have minus 3 times 3 over 2, this is equal to minus
4.5.
minus 4.5. Okay, we got it. So we have the same coefficient, minus 4.5. That's good. We got this one too. Then we can define a matrix A, which is equal to minus 1 to the power I plus j minus 1. Okay, and then the matrix be 3 by 4. Matrix A, which is 3 by 4. What is the rank of this matrix? Well, let's write this here. What is A11? A11
minus 1 to the
Minus
first
1.
power plus 1 plus 1
0.
minus 1. Yeah,
Yes.
it will be 0.
0. What is A12? We get
1 minus 1 plus 1 plus 2 minus 1.
Is it 3?
just
1.
I think it's 1. So actually, let's try to understand this one. What happens? So
Then a 3, then it will be a 2, then we will be a 3.
you mean here 2, 3? 2,
Yes.
3. Well, let's check. I'm not sure, but let's see. Actually, when I is an odd number, that means that this is the first column, right? A1. No, this is the first row. When I is the row, which means that for the first row, this is always going to be minus 1. Minus 1, this will make it minus 2. Minus 2, then this would be 2, I think that's 2. 0, 1, 2, 3, right? This is correct, it looks to me. Then, for the second row, so let's check actually A13. What is A13? This is minus 1 plus 1 plus 3 minus 1. That is correct. We get, no, wait a second. We get 2 then.
It has to be 1, I think, minus 1 to the power of 2.
No, but I is 1. Minus 1 plus 1.
I thought of the second row, you meant it. Sorry.
Okay.
Yeah, we're correct. 0 plus 3 is 3, minus 1 is 2.
I cannot
That's
think.
correct.
So this is 3 or 2?
No, that's equal to 3. That's okay.
Yeah,
A1, 3 is the 2 you have written over there.
yeah, that's true. That's true. Okay, that's 2. Okay. Then, if we go to the second row, we get here 1 minus
2, 3, 4. And then 2, 3, 4, 5, I guess.
Well, let's see. Because this is going to be the third row, this is minus 2. It will start from minus 2, then we have 3, 1, 4, minus 2, 2. Okay? 2, 3, 4, 5. To me, this is what I can come up with. Most probably this is correct. And then, let's see what is the rank of this matrix. To check the rank of this matrix, we got a 0. Maybe it is best if we switch row 2 with row 1. So we can get here 1, 2, 3, 4, 0, 1, 2, 3. And then let's try this one initially. 2, 3, 4, 5. Then let's subtract from the third row twice the first row. So if we do that, 2 minus 2, 0. 3 minus 4, minus 1. 4 minus 6, it's minus 2. And we have 5 minus 8 minus 3. Okay, this is the third row. The second row remains the same, 1, 2, 3. So what can you say about the rank?
We can divide
rank
the
is
third
1.
row by minus 1 and the rank will be 3. No, the third row is the same with the second row.
Yes. So we can produce zeros here very easily. Потом гледаем решение на третьем. Туда лицево паста. Okay. So it looks like we have two leading ones. If we have two leading ones, it looks like the rank of A, which is defined like this, is 2. Okay. So the rank of A is going to be equal to 2. Now, other than this, what is very important is also the relationship between the rank and the number of unknowns. Okay? So let's think for a moment that we have 5 unknowns and 4 equations. Okay? So let's assume for a moment that we have a matrix A 4 by 5. A 4 by 5. What does this mean? A 4 by 5. How many equations do we have?
4 equations.
How many unknowns?
5 unknowns.
5 unknowns. Good. Now, it can happen, we have seen it a lot, that one of the equations here could be dependent on the other 3, right? What does this mean then? This means that this would be 3 equations, okay? And we still have 5 unknowns, okay? Now, if you have 3 equations, so this one, we see this when we have the matrix A. We see this when we have the reduced row echelon form of A. This, we can, at this point, we can make these conclusions. Not conclusions, we can make, it's useful to make such an observation at this stage. So if we have 5 unknowns and 3 equations, can we solve the equation?
Can we what?
Can we solve the equation? We have 5 unknowns, 3 equations. Can we solve it?
No, we probably can't.
Solution.
We need the same number of equations as unknowns to solve it.
Okay, so that's true. We need 5 equations for 5 unknowns, or 7 equations for 7 unknowns. But we can have less equations, but then what we are going to get is that we don't get a unique solution. We get a plane.
We either get infinite solutions or we get no solution at all.
Okay, so in principle, when we have 3 equations with 5 unknowns, if we have 3 equations, how many leading ones do you have? Sanisha, Kevin, Philin, Tožnoriešte. Okay, 3 leading ones. If you have 3 leading ones, that means that how many variables are free?
2.
2. So here we have 3 leading ones. So it looks like there is a relationship, and these 3 leading ones, this is actually the rank of A. So it looks like if we have a matrix and judge it by what the rank is and what is the number of unknowns, we can conclude into the correct number of what is the free variables and many more. So just for a moment, let's check. So in principle, we can say the following: the number of unknowns, we can say n is equal to 5. Okay, whatever n is. If the n is equal to 3, then free variables. Let's say free variables. This would be equal to n minus r, which would mean equal to 2. Okay, so let's keep an eye at and what happens if n is equal to r?
And there is 0.
There are no free variables. We have.
Well, we could also say this, right? When n is equal to r, we can have a unique solution. Okay, this we can also report this statement. Would you agree on this one?
What?
Would you agree on this statement? So when n is equal to r, then we have a unique solution.
Yes.
Yes.
Any objection?
No.
Okay, then let's see if we what we can do now. We could. Okay. Now I think in this session we also discussed. I think we discussed about whenever we solve a system, we look at the rank of A, right? Rank of A and the rank of B, right? Whenever we said that when the rank of A was equal to the rank of B, sorry, not B, AB. We also mentioned this one. When the rank of A is equal to the rank of augmented matrix AB, then we have a solution. Or it's consistent, okay? We have a solution. We discussed about the range.
Charge quadrature para solution?
Have solution. We have a solution. Or we can call this one, it's a consistent system of linear equations. Actually, let's assume that we have an augmented matrix which looks like this: 1, what if we put here a 2? What can you say about this system?
Has no solution.
Okay, has no solution. So this is something which we should distinguish straight away. But let's assume that we have a solution. We make it 0, and we look at the final reduced row echelon form, and we obtain the following information. So we have simplified this as much as we could. It looks like we were successful. And then we try to write wait a second. Okay, so let's try to solve this. But in order, if we want to solve this, I guess we can simplify this a little further, right? So we have a leading one here, a leading one here, and a leading one here. And we need to make all zeros in the columns where the leading ones are. So in this column, we have only 1, 1, and all the rest are 0. So this is good. This is done. When we look at this row, we have this 1, but we need to make this -2 also 0, using this equation where row 1 star will be row 1 plus 2 times row 2. And then, once we do this, we have to look for what we are going to obtain. So normally, we get here 1, 3, 0 plus 2 row 2, right? Yes. 0 plus 4, this is 4, 0 plus 6, okay, 0 plus 2, this is what we get. Then we have here 0, 0, 1, 2, 3, 1. And, okay, I think we did this part. We completed this task. But then the next task that we can use is the following. We can try to produce a 0 here for the moment. Or, let's see, for the moment, yeah. Here, we have the row 2 star would be equal to row 2 minus 3 row 3. And then this one is not going to change. Yes? Now,
Can't we subtract again row 2 from row 1, because we can remove the 6 at the end. We don't need the extra operations, I mean.
with this one here,
Do something like yeah. Yes.
we subtract row 2, say it again.
Row 1 equals to row 1 minus 2 row 2.
Minus row 2. If we do it like that, you mean here now?
2 row 2.
Minus 2 row 2. Why? To make this 0.
Yes, we remove the 4 and the 6 at the same time.
Minus 2 again we had there before.
I think we can use row 3 because there's only the one
Yeah,
there.
we go back
We
to
want to
the
reduce the
start.
6.
Take it easy. Okay, eu tiro para here.
We can use row 3.
We can use row
There's-
to make these zeros, right?
Yeah.
Now, this is done. This is done because we want to make zeros at the leading ones. So that's essential for us. Then we can check. We can use this one to produce a 0 here and here. How can we do it? We can use row 3 as a pivot. So having here a 0, it is not, well, it is important, but we have to do it through this. So here we can say row 1 star is equal to row 1 minus 6 row 3. And row 2 star, this is equal to row 2 minus 3 row 3. In this case, we look at 0, 0, 0, 0, 1, 5. And here we have the following, we get 0, 0. Then we have row 2 minus 3 row 3. So we have here, this is 1, 2, 3 minus 3, 0, 5 minus 15 minus 10, okay? And then we do the final operation, which here we get 1, row 3 as a reference, right? Can you correct me if I make a mistake? 0, 4, we get 6, wait a second, 6 minus 6, we get 0, and then we get 2 minus 30 minus 28, okay? So it looks like we completed our fundamental task. So these are all zeros. Sorry, it's here, and we have completed. So this is the simplest way that we can do. Then I think from here you can move ahead and find out that x1 plus 3x2 plus 4x4 plus 4x4 is equal to minus 28. But before we do this, we look for what are the leading ones. Leading ones are here. Now, which one are the free variables? We have here x2 and x4. So these are free variables.
Isn't it minus 14, not minus 10?
Say it again.
Isn't it minus 14, not minus 10?
Here. Well, let's
Yeah.
check. 2 minus 30, because this is minus 6 row 3.
The second row, Professor.
No, in the second row,
Here.
It's 1 minus 15.
Here. Okay.
Yeah. 1 minus 15, it's 14, not 10.
That's true, minus 14 is here, right?
Yeah.
Okay, that's better. Thanks. So here we have 3 leading ones, but we have 3 variables. We have x2 is equal to s and x4 is equal to t. So we can use them like this. And if this is the case, could I substitute them right away? It is x1 plus 3s for x2 plus 4t plus 4t. And then we have in the second equation, we have x3 plus 2t, this is equal to minus 14. And finally, we have, what is x5? What can you say about x5?
It's 5.
It is a constant value, okay. Then, let's write the answer. x1, x2, x3, x4, and x5. The solution of this system, this is equal to the, let's write first the constant terms. What is the constant term for x1?
Minus
8 plus s plus t. So x1 is minus 28 minus 3s minus 4t. x2 is equal to s, which is just 1, 0, 0. x4 is equal to t, which makes 0, 0, 1. And x5 is equal to 5. Yes, 0, 0. So this is the solution. Now, what do we observe here? We observe a condition like this. We started with 4 equations, but one was redundant. So we get 3 equations, 5 unknowns, and it looks like we have 2 free variables, and 2 free variables that produce, these are the 2 free variables. So it looks like the solution space is a 2-dimensional structure, okay, it's a plane. And from here, we observe that, this is an example of how to obtain this unique relationship between n, r, and the number of free variables. Okay. Yeah. Okay, so this is all for today. Do you have any other question?
No.
Can we assign t or s to any variable, or does?
I think you're free to do. Did you mean this?
No, I meant. Can we put t and s to any other variable except x2 and x4?
Well, we put these indices mostly for the, what is the name? For the free variables. This, okay.
Okay, understood.
Maybe I didn't understand the question. Sorry.
No, I got it.
You got it? Okay, that's good. Okay, so any further question? If not, that could be, yes, I'm still here, but if you don't...
Professor, about the range of this matrix.
Oh, the range of this matrix.
Yes.
3.
Well, that's true. The range of this matrix, it is in R3, okay, let's use this part of the board. This is a good question. So the range of this matrix is the following, but we're going to come to this issue a little later. So range of A, it is described as, let me put it like this. So we have constant C1 times 1, 0, 0, plus constant C2, 3, 0, 0, plus, is it worth writing this like this?
No, because one vector is a multiple of the other.
That's true. Let's go ahead. We took it out. Plus C3 times minus 2, 1, 0, minus 2, 1, 0, plus C4 times 0, 2, 0, 0, 2, 0, plus C5, which is 0, 3, 1. No, well, yeah. This is not the simplified version, but we can write this one 0, 3, 1. In fact, okay, we wrote it like this at this stage. I guess we can continue again here. This will be C1 times 1, 0, 0, plus C2, 3, 0, 0. So we're trying to, now we wrote this one looking at this stage. But let's write the same thing looking at the more simplified version. Do you agree with this? Plus, so it's clear that this will be redundant, okay? It doesn't make sense to keep in the spanning a space using vectors that look like this. And by the way, this is R3, which is like the 3-dimensional space, because we know that if we define x, y, z, we define something which can constitute a volume. So let's see here, C3, what is C3? 0, 1, right? I'm reading this here. Plus C4, sorry, I'm forgetting a lot of things. This is 0, 1, 0, okay? Why don't you remind me? 4, 2, 0. And C5, which is 0, 0, 1, 0, 0, 1. Okay, so what? No, I have another.
C3 is should be 0, 1, 0.
0, 1, 0. Yes, I know this now. Okay, so which one? Let's see which one is the most. What can you say? Do you observe any other essential element here?
Can we remove the C4?
That's a good choice, but why?
I just kept the vectors with the 1 and zeros. So.
Probably, if you combine C1.
Yes, if you combine them. So.
That's true. Can you simplify anything further?
No.
No.
It doesn't get any simpler. So actually, that was a good question. Thank you for asking this one. So what is the range of A? Because we observe that the range is really the x, y, z. They are the orthogonal directions for three-dimensional space. Okay. So this is x, y, z. I guess you can read this, or we can rewrite this one somewhere here. So we can say that the R of A is equal to any linear combination, or let's write it like this. Linear combination, we denote it also like this. You are going to see this notation at least a couple of more during the semester. We're going to see it again. Okay, so this is the range of A. Is it clear? So, yeah. Probably, wait a second, probably it was. Okay, any other question? But it has to be.
I was just confused because I thought for a moment from the parametric equation we could get the range and it would be r squared, since the parametric equation represents a plane, the one that we got in the end.
Okay, but that's the solution. Those are the points with which you multiply.
It for me.
Okay, it's good. Okay, but that's it's also good to draw that conclusion. It's interesting because it looks like the dimension of the range plus the dimension of the solution, they look like it's equal to 5, right? So we can look here. What is the dimension of the range of A? Well, it is equal to the number of leading ones. Let me write it like this, which is the rank. But you see that the way that I mean, a lot of the material is really intuitive, so we can obtain fundamental outcomes or results even at this stage, which is not that it's not that super difficult, but it's good that you are working on the intuitive or the intuition of the whole matrix constructs. Okay. Any more questions?
Are the numbers of the dimensions of the range equal to the numbers of the leading ones, because essentially every vector can be described with 1 times a certain number?
Well, the dimension of the range, first of all, as we said when we first defined the range, it depends on the number of rows of the equation. Okay, so we could have, right? So we said that if the matrix is A, n by n, then the dimension of the range, it is n. Dimension of the range of A, this is m. Because if we have a matrix which has 3 entries, we need a triplet of numbers. If we have 3 rows, or sorry, if we have 3 rows in the Is it clear, or did I answer it? I think if you go back to the definition of the range, you can see it from there. Okay.
Yes.
Okay then. I think. Any more question? Okay, I guess if this is all, we can close this.